So we're going to start on classification this week, and there'll be three sets of slides associated with classification because it's kind of a big topic. And the first one will be the basics, kind of what is this, and then we'll get into unsupervised classification, which is also known as just clustering. The second lecture will be supervised classification. And the third one will be accuracy assessment. So how did we do with our classification? So for starters today, I will talk about the what and the why, and some issues with even kind of getting started. Then spectral signatures and their variability, what is spectral space, and then this introduction to clustering and one algorithm called k-means clustering. So why and how do we classify? Well, we sort of know at this point that these sensors are really just detecting a bunch of photons. And so different land covers are depicted just on, some kind of gradient of spectral radiance that isn't necessarily, useful as far as information. So it's a starting point. But what we really want to do is we want to get to categorical or nominal land cover classes in order to be able to, actually get some actionable information. And so this kind of leads us to the benefits of this whole process. We're simplifying, like no one wants to see a spectrum of vegetation and have to know about SWIR and NIR and VIS. Like they just want to see a map of that something is a certain tree species or a certain land cover. And, that output is more actionable. For this map over here, I can now very easily tally up, all of the native tree species in Santa Barbara, these Quercus and Platanus trees, for example, and do, some sort of spatial analysis on the planting patterns of eucalyptus and jacaranda. So it's actionable. Facilitates scaling of local results to larger areas. So the local results mean like on the ground, like you went out and verified the location of certain cover classes like water, grass, tree. And once you use those to train a classification algorithm, you can then make a map over a larger area that's very, difficult to visit in person. So that's maybe the most kind of basic useful goal of classification. And so this process is semi-automated, meaning you don't have to look at every single pixel of the image you want to classify manually. You let an algorithm do it for you. So here's just an overview of the process that we'll go through. So starting by, defining what your objective is, like what do you want to map and why? What are the useful classes? Do you want to just map all grass, or do you want to differentiate dead grass and alive grass for some reason? Do you want to just map all trees, all forest as one class, or do you want to divide up your map by tree species? So it's what is your goal in this process? Then the hardest part, this is the hardest part of the whole process, is training. This means you have to have some information either from physically visiting places on the ground or using something like Google Earth imagery to train the algorithm to know what the truth is in certain locations. And then this is kind of the stuff that you do in Envy. So you gather statistics about your different training classes, you actually train your model and do the actual classification, assess your accuracy, and then you've got a final product. And so I'm sort of zooming through these for right now because we'll visit each in depth. So taking a step back here before we dive in, just, what are some of the common uses of this? These are just, there are myriad classifications, but these are commonly used ones at the global level. And so what you're seeing here are all the different classes that are being mapped here. And so you've got, things like irrigated agriculture, and you've got deciduous open tree cover and, all these different tree classes here, shrub classes. Partly this is going to be what's important for people to know about global land cover. And frankly, part of it is based on what's possible to measure from a satellite. From as far as approaches go, this particular map, this GLC 2000, was bottom up, meaning there was lots of training data provided from field plots by a lot of experts in local areas. So, someone was here. There's lots of training data, so you actually know what's on the ground at lots of different points on this map. And so that's, very difficult. Like, do you really have people out there sending you training data or not? But it leads to a pretty accurate map. On the other hand, you've got this MODIS global land cover map. And so MODIS is a satellite like Landsat, except for it maps at about 500 meter pixel size, but every day. So that's kind of the pro and the con of MODIS. And so this map is just made this top-down approach, meaning it's really just training on a limited amount of ground data and mostly just making new maps every year based on the actual information at the MODIS sensor. So, of course, this is going to be less accurate, but it is automated. So it's better for looking at change, of course, but not necessarily your best go-to product for a single day. So there's many challenges to doing good classification using remote sensing. And some of them are just even conceptual, not even getting into the technical stuff here. But like, first of all, what are we mapping? What are we hoping to map? And what can we map? Are we mapping land cover, which is actually the stuff, the material that you're seeing on the ground? So this could be, forest, sand, open water. It's just what the satellite is actually seeing, a building, asphalt. Or do we care about land use? Frequently, we care a little bit more about land use. But, this is things like commercial, residential, abandoned lands. But how do these things manifest spectrally? Well, they're going to really manifest as these kind of land covers. And we may have to be creative to think about how we translate land cover to land use if that's ultimately our goal. Because remote sensing, much better at measuring land cover because that's what the light is reflecting off of. The light isn't reflecting off of commercial. The light is reflecting off of a mix of buildings, cars, roads, vegetation across some amount of space that comprises a commercial area. So, just looking over here, you've got things that look quite similar in at least RGB, visible wavelength spectral space. And, how do you really know the difference between one of these is irrigated agriculture and one of these is tall grass prairie? They may look spectrally quite similar, but they have very different ecosystem function. So it's always a challenge. Same deal over here. Do you have a city beach in Santa Barbara or do you have the Sahara Desert? Honestly, I don't even remember which one is which anymore because they're both just a land cover of some type of sand. Down here, you've got the conceptual difficulty of differentiating industrial landscapes from commercial. And, you probably have some visual cues here. For instance, the fact that all these vehicles are the same color may be more likely to be industrial versus just normal parking lots for commercial. But how do you differentiate? How would you classify those landscapes at the pixel level just using spectral information? Again, it's challenging. And there's more issues. So another issue is that of scale. So what is the scale at which you care to do the classification? So is it something, very zoomed in, like the material scale, where you're actually, in this image, you can classify the bark of a tree. NPV is just non-photosynthetic vegetation, kind of what people say in the remote sensing world for tree parts that aren't photosynthesizing, versus this other material of green vegetation. So in this image, those could be reasonably well differentiated, but do you care? Or do you just care that this whole area of a bunch of trees would be considered forest? And so this would be more starting towards your biome scale or local scale mapping, which is probably more common in remote sensing. And it relates to this issue of mixed versus pure classes. So, what does this mean? What does it mean to be a pure class? Well, it basically, it's a fuzzy definition, but, is the spectral signature of all pixels within a class reasonably similar? So if it's a road, they're probably mostly pretty similar. They're going to be some sort of asphalt spectrum or something. But even this pure is in quotes because, well, if you're looking with a high resolution imager, you could maybe see the yellow line in the middle of the road, and that's going to be a different color than the rest of the road. Some road parts might be bright white concrete. Some of them might be deep dark asphalt color. So even there, road could have multiple different spectral signatures. On the other side of the spectrum here, you've got a very mixed class where there are a bunch of different spectral signatures. So, you've got these bright white buildings here. You've got a lot of vegetation overhanging other road surfaces. And so you have many different spectral signatures that are going to be very different, comprising a single land use class. And so that gets complicated. If you wanted to assess dense urban at 1 meter resolution, you're going to have all of these different pixels looking very different from each other. However, dense urban you could actually benefit from having a 500 meter pixel that actually blends everything in this box together and takes an aggregate, a spectral signal that actually is accounting for the amount of vegetation mixed with the amount of impervious surface, and you may get a decent dense urban spectral signature. It's possible, at least. Finally, hard versus soft boundaries. So does it even make sense to have crisp boundaries between classes? So why don't you look over here? And again, this is sort of like the Nanjing project here of where do you draw the boundary? Do you say that everything over here is urban and everything over here is rural? Maybe that might suit a certain application, but sometimes it's better to not classify at all and actually just look at abundances, meaning in this case, how much of a pixel is made up of vegetation and how much of a pixel is made up of impervious surface. And with those fractional abundances, you can actually do a continuous map of urbanization, continuous as opposed to categorical, which would be your straight urban versus rural classification. Okay, so using something like Landsat or MODIS, the whole basis for classification is differentiating pixels from each other in spectral space. And I'll get back to that spectral space term in a second, but it's basically how different are the spectral signatures. So this is just a spectral signature here, or this is multiple spectral signatures of forest. And we know, it's a signature. We can recognize it. We can say it. It's like you signing your name. We can look at that signature now and we know that that's forest. We can look down here and, at this spectrum here, and we can say, well, that, it's probably some kind of impervious surface. So what I'm actually showing here is this idea of, how kind of consistent are the spectra for a given class. And so what you're seeing here is the mean spectrum and the range for 10 forest pixels. And particularly if you look down here, you see that the variability within these 10 forested pixels for red, green, and blue is quite low. So low within class variability. That's a good thing. So that means that forests look fairly consistent in those wavelengths. And even up here, in the shortwave infrared and near infrared, you'll come to see that amount of variability, that range for those 10 pixels is not too bad. This is a pretty tight clustering, which is going to make it easier to differentiate from other stuff. And you can see that consistency in this actual image. Not much variability in Rock Creek Park Forest. Move down to grasses, and you can already see, even though all of this is grass, you've got some mix of dead grass and live grass that manifests as much higher within class variability of the spectrum, which is going to make classifying grass a little more problematic. So in here, your mean spectrum, which is here, is actually a mix of live grass, where you see that there's good red absorption because it's photosynthetically active. And you're also seeing dead grass, which is not photosynthetically active. So this becomes a tricky class, and you think, well, it might actually be better to make a live class and a dead class because there's such a range of spectral signatures within this signal class. Urban is even worse because you can see it's a mix. It's not just like dead versus alive. It's bright buildings, dark roads, live grass, sort of, senescing trees. This is probably from a fall image. And so you can see there is huge variability in urban spectrum when we're just taking these 30-meter pixels here, wherever, because they are entirely different things that we're measuring. So again, that's why dense urban might be a tough thing to classify at the individual pixel scale. So let's take a step back. I mentioned spectral space. That's kind of the space in which we're operating. But what is that? Well, let's start with just geographic space. This is how we normally think of space. Space is just the kind of distance between, how much space are you going from Venice to Moscow? Well, you're traversing some amount of longitude and some amount of latitude. Whoops, those are wrong. Those are flipped, right? And this ultimately, you're moving some number of total kilometers in geographic space. Now, the same thing applies in spectral space, except for in this case, the addresses, instead of being cities or latitudes and longitudes, the addresses are in terms of reflectances. And so this is just a 2D example, but basically, this dense vegetation right here has some sort of address in red. Red and near infrared space. So that is roughly its address, whereas bright soil has a very different address. So more like 2500 and 3500. And so those addresses are pretty far away from each other in reflectance units, which ultimately will lead to a higher ability to differentiate veg from bright soil since they're far away. So keep in mind that I'm just showing you a 2D example because that's what we can see easily on a PowerPoint slide. But these distances can actually be an n-dimensional space where n is the number of bands available to you. So, 3D, you can picture this in a cube, but beyond that, it gets kind of wonky, crazy, who knows. 224 dimensional spectral space sounds like it's out of sci-fi, but the math still works out. And having all of these dimensions allows you many different dimensions in which to differentiate two objects, two different material types. So let's look at just one example of an algorithm for how different materials might be differentiated using just automatic clustering. So I'll kind of revisit the difference of unsupervised and supervised classification as far as the definitions a little later, but right now let's not even worry about that. So all we're doing is we're searching for natural groupings of materials or cover types in terms of their spectral properties. So in this 2D example, we're just band X and band Y. Doesn't matter what bands they are for right now. And so we're going to look at the k-means algorithm to do this. And an important thing to note here is that we don't know what the classes are beforehand. So that we're not training a classifier. We're just letting the proximity of these various points form natural clusters. And clustering is not just possible in 2D, but it's also possible in n-dimensional feature space. So why is this algorithm called k-means? Because you decide initially how many, or k, clusters are likely present in your data, and the cluster centers are defined as the cluster's means. And so in this case, these are the K's kind of after clustering has happened. So it's going to be easier to see once we run through the example. So let's just do that. So first step is define your target number of classes. Well, in some place like, out in the countryside outside of DC, I would say, okay, there are likely 3 classes, and they are water, forest, and soil. So this is just sort of me thinking what's likely the classes are in advance. I might be wrong, though. So forest, bright soil, and water. Now, the first thing that happens after you define your classes is that your 3 clusters, because you said there are 3 classes, so these 3 cluster centers just randomly get thrown into this spectral space. So they get some near infrared and some red address that may not have any relationship to the data. So now step 2, now we have the algorithm doing its thing here. Step 2 is the data, which is just pixel values, are assigned to clusters based on minimum distance to a cluster center. And so you're seeing this assignment with these boundaries here. And so these boundaries are defined by what cluster center you happen to be closest to right now. And so all the green pixels are assigned to this particular cluster right now. These guys are all assigned here, and these guys are all assigned here because it is less distance to get down to K3 from this pixel than it is to get up to K1. And so that's the minimum distance. So these are all these pixels are now classified, just as K3, K2, or K1. But this is just a first iteration. So this is an iterative process. So the next thing that happens is the cluster centers now migrate to occupy the mean center. That means, so mean NIR and mean red. it migrates over. So this guy moves over here because of this cluster of green things, the mean NIR value is going to be somewhere over here, and the mean red value, so that means, the distance, the average red value is going to be somewhere over here also. So it's going to move left and right and up and down to find the new mean of all of these green pixel values. This guy moves down here, and K3 moves over here. So the cluster centers have moved, so we're seeing that movement, and now we have the next part of the iteration here. So we have a reclassification based on these new cluster mean centers. So this guy used to belong to K1, but now he's actually going to be closer to K2. So these are all the ones that now get reassigned because they're now closer to different cluster centers. And so, particularly these ones seem to make sense. They would kind of fit into this broader cluster, as to previously, this guy was over here and this guy was up here, but maybe that doesn't seem quite as intuitive. So this iterative process puts pixels in probably more intuitive clusters. So we keep doing this. You can keep iterating, but it's usually fine to only do it, like 5 or 10 times until nothing changes anymore, or the user just says stop. So we've got our final cluster outputs, and then it is your job as the expert user to say what those probably are. And so in this case, say bright soil, forest, and water. Of course, still have some error. That might be atmospheric contamination or something like that. So we will give this a try using R.